is, you can have latent class models where you assume that it's not continuous, but it's a discrete grouping, kind of like the Poisson model we talked about, the zero inflated. That's kind of a latent class where you're either a person that has no probability of event or no possibility of an event, or a possibility, and I don't know which one you are. So you could introduce that, and of course that can have different levels. Latent class are often used in education models. Try to capture like groups of types of children, kind of thing, from testing results. As various ways it's used. We're not going to do latent class except for just mentioning the zero inflated Poisson. So we'll condition on some continuous characteristic that we assume is randomly drawn from the population when I draw the person, and then we assume then the outcomes are independent of each other when I conditional on the covariates and whatever this latent variable is. And that allows us to draw our likelihood like a product. So this comes next after we discuss G. Just to point out, they're not mutually exclusive. You can have a transition model that's a mixed model. You can have a transition model that you're fitting with GE. Like they're not necessarily mutually exclusive. They can be combined. And just to re-emphasize this point, fitting these models doesn't guarantee you're separating out the actual longitudinal effects from the cross-sectional effects that we discussed before. That's more of how you fit the regression model to find it, not so much the likelihood or the method to estimate the coefficients. So this is always important to remember. This is a little bit early to introduce this, but we're going to use another simple data set. This is just continuous outcome data on dental distance, so looking at like how the distance between teeth grows when you age as boys and girls. And that, I think it's used for braces, like when it's a good idea to get braces when you peaked. Anyway, it's convenient. It's a small data set, and it's got this nice repeated measure structure, longitudinal. I could just say I want the difference by the end of 14. What is the mean distance for girls minus the mean distance for boys at age 14? But I'm going to use the slope to fit it. So I'm not just going to take the observation at 14. I'll use the whole thing, predict here, predict for girls, and compare that. That's something that makes sense regardless of how I fit the model. That's still something that will have a smooth sampling distribution. So that's the issue, is that when you don't a priori choose what you're going to report before you fit your model, then your parameter report becomes data specific, and you're not even technically, in reality, your sampling distribution becomes undefined. Sometimes you have this parameter, sometimes you have that parameter, right? You could imagine doing a bootstrap and trying to give it, because bootstrap doesn't work unless the sampling distribution is normal. So it gives you some idea. Sometimes 20% of the time I reported just an average slope, 80% I reported separate slopes. That may give you some more information. It's not technically inference, like a confidence interval. But it's always an issue. Like that's why causal inference is so compelling, because you specify a parameter that has nothing to do, it's non-parametrically defined. You're not defining it with respect to coefficients. It's like I want the mean here and the mean when everyone's treated versus the mean when everyone's not treated. And then I can fit the data the way I want to in that context, because my parameter isn't a function of the model I'm fitting. And that's the way a lot of the analysis is going, right? That's more and more people are saying, okay, I want to define something that has meaning that's separate from the model. And I want to be able to fit the models, not assuming any linearity, because who knows? Sometimes it's right, sometimes it's not. And so I get more robust, less biased estimates and more robust inference. The problem is, oftentimes they're black boxy, right? You get a machine learning algorithm that fits it. Then you say, typically what you do, this is like a rough idea how you might do causal inference. I would fit machine learning to this, including age and gender. So it might have all kind of complicated polynomials or trees or whatever. then I would say, okay, I want the effect of, let's say, I mean, this isn't a perfect intervention, but let's say I want an effect of girls, the impact of girls. So I change everybody indicator to 0 and predict the outcome at, let's say, at 14, based on the model, and get the mean of that prediction. Then I turn everyone to boys, so turn everyone Xij 2 to 1, re-get that prediction. Now I have the average of the outcomes at 14 when you're a boy versus a girl. I can compare them, right? The reason that people often are, I think, reluctant is people like to see a model, right? It kind of feels uncomfortable if it's a black box. Like some of these algorithms that you fit things with are, they don't really produce a model you can see. You can do things like variable importance that are post hoc examination of the model, these kinds of things. But that's kind of the bridge, that's kind of the gap we're at right now. So we need more diagnostics to make people comfortable with the black box and make sure it's correct. So it gives you some interpretability. So there's a big field of interpretable machine learning, or AI, that's trying to kind of solve this issue in some sense. It's not solvable completely. It's going to always be a little ad hoc, but yeah. So that, now in this case, everything, I could fit this non-parametrically. I wouldn't have to, I could fit it both interpretable and non-parametric, because it's all, I have ties at every age. I could get the mean dental distance for girls at every age and boys at every age, and I could make that my model, right? I could just say, okay, the mean of the outcome if you're a certain gender and a certain age is just based on the mean of that age, right? So in that case, when you can fit things non-parametrically, there's no issue anymore because it's both interpretable and I can't be more flexible, because yeah, that's the fitting the data. That's just fitting the data directly, right? All great questions. It's a little beyond the scope of the course, but I like getting them because I think they're important issues. And I really think we need a model selection course in the School of Public Health. I think it would be very helpful. Kind of try to would both talk about model selection and its pitfalls and how you could do it in a way where you pre-specify something of interest beforehand, but still fit parametric models, and maybe it goes eventually to teaching how to use machine learning to fit your models. So maybe in the future. So anyway, if we took this data, let's first start in the context of maximum likelihood. Let's assume, and we'll do that to show you how the estimating equation is evolved from the likelihood. So we have Yij is the outcome measure of the ith child at the jth time, and these jth time are regularly measured. We have two covariates, which is the age of the child, and we have the gender of the child. So the gender of the child is binary, arbitrarily 1 male, 0 female. It could be the other way. We'll fit the data exactly the same, or the coefficient would have a different interpretation. And so we'll assume some linear model with an interaction term. Why do I put that there, do you think? Why would you add gender times age? What does that imply? If this coefficient is not 0, beta 3, what does it imply about the slope for girls versus boys?
But there might be a different relationship.
Yeah, there's different slopes. That's what it implies. So it allows there to be different slope for girls, average slope for girls and average slope for boys. And of course, a test of that would be the test that beta 3 is equal to 0. If that was 0, then that would imply they all have the same slope. Yeah?
There, if, for example, beta is equal to 0, will that have an effect on the model if I've included? Or I could just...
Would it have
So my question is, if there is an effect, what is the impact or included or not including that particular element in the model, given that that is true or false? You know what I'm trying
Yeah,
to
I think I'm trying to. So, it's easy to answer that in the context of a priori specified. I believe there's interactions, so I'm going to put it in. You're asking, what if I have it in but take it out? Or
Yeah, exactly. So if I don't know if they matter and I don't include them, will that have an effect on the general
Yes, this is the point I made earlier in the course, exactly. If I look at this, if I take this particular data set, I do a test of that mean equal to 0, and I have a p-value that's not small. So, meaning it's big, so I don't reject the null, and I take it out. And then that would change what I report, right? Because now I'm reporting, let's assume if I report that, all I need to report then is the beta 1. This gives you a different intercept. So in other words, the slope for boys is beta 0 plus beta 2. The slope for girls is beta 0. But this has a slope for both. So if I had this in, I typically report the slope for girls separately from boys. So for girls it's beta 1, and for boys it's beta 1 plus beta 3, right? If I keep, well, depending on what I hold, yeah, it'd be beta 1 plus beta 3, because it's binary. And therefore, I don't technically have a sampling distribution anymore, because if I get a new data set and and repeated samples, if I theoretically took another group of children, followed them same number, same times, and then this time it was below 0, then I would report separate slopes. So it means that in repeated samples, I get different parameters depending on my data. And that's always a problem for defining your sampling distribution. That's why it's best always to say beforehand, maybe you want I could define something like the average slope. Even in this model, I could define it, right? I could take beta 1 and beta 1 plus beta 3 and add those together, divide by 2, that would be the average slope, right? And that would make sense regardless of how my model turned out.
Okay,
So that would be more likely to have a more normal type sampling distribution. If a priori said, all right, say I want to know the difference. Let's go back at another example. This is important, although. So again, we're going to fit this. This is our parameter. Just to point out, we're going to fit it with ordinary least squares, right? And I'm going to go over that in some detail. I don't expect you to memorize all the technical detail for it for sure, but just get the gist of it. So it can be motivated in two ways. One, if I specify a particular likelihood for the error term, when I have this plus an error, I can use maximum likelihood. It can be based on whatever I assume about the distribution of the error term. I can write down the density of the probability or the density of an observation given the covariates, and then I can solve the likelihood. I also can look at the OLS you get directly. You can show it's unbiased regardless of the distribution of the error term. So that's the estimating equation approach, where I'm just saying I'm not specifying what the error term could be. It could be, it could be symmetric. It could be slightly skewed. It only has to have mean 0 given the x. So what is max likelihood estimation based on? Is based on score equations. So you have to define the likelihood, right? Which is like in a cross-sectional case, you get the probability of the first observation times the probability of the second based on the parameters and the data. And then you take the log of it, and that ends up being a sum, right? Because if every observation is independent, the probability of them all is the probability of the first one times the probability of the second one, etc. And then we do classic calculus. I want to solve that likelihood. It's if theta is one dimensional, it'll look something like this. So this is the log likelihood. And this is theta hat. And you find the maximum likelihood, and that turns out to be your estimate, your maximum likelihood estimate. You can see it in one dimensions easily, right? I can just plot the likelihood versus theta, go to the maximum. Now there's ways to do, the computer can do this that you don't have to do it manually, right? There's ways of climbing these things to guarantee you at the top. In this case, it's even easier because I can just solve this analytically. I set this equal to 0. I want to find where the slope, that's the slope with respect to theta, where it's 0 because that's at the peak. And then I set it 0 and I solve for theta. That gives me a maximum likelihood estimate. In this case, turns out oftentimes you don't get just theta on one side and the data on the other. There's theta on both sides, and you have to keep on climbing up the likelihood. You can't solve it in one step, right? That's why sometimes when you do maximum likelihood, they'll see the iterations because you can't just do it in one step. But linear regression, it turns out it's an analytical solution. You can solve it in one step. So just, again, not terribly important, but just to get more tangible feel for what it looks like. So I'm assuming my error term is normal with mean 0 and some unknown variance sigma squared. If I look at my likelihood, it's just a single observation. If I'm and I'm assuming they're independent now. So just for one observation, this is the likelihood. This is the normal 0, 1 density. That's what that small phi always means, almost always. So and this is y minus the predicted value of y based on the current coefficients and the covariance you measure on that, the age and gender, divided by this. So this makes it a normal 0, 1. I'm taking y, I'm subtracting its conditional mean, so now that has mean 0, and dividing by sigma, so it has standard deviation 1. And so that is for one observation. If I take the log of every observation, first of all, if I take this for every observation, the likelihood is just the first one times the second one times the third one for every observation within every person, because I'm assuming independence now. We're going to generalize that, but that's what we're doing now. If I take the log of that, I get this. So this is the log likelihood. It's a sum of the log of the density, normal 0, 1 density, where this thing you can think of as just kind of the residual, right? This is observed minus predicted. And then this is the unknown residual standard deviation. Anyway, that's what it looks like. So what would you do next? I would take the derivative of that with respect to the betas. So I get the partial derivative with respect to beta 0, partial derivative with respect to beta 1, all the way through beta 3. And then each one of those gives me a different square equation for each parameter, set them all to 0 and solve them. And it turns out when you do that, you end up with matrix operations, but it can solve it in one step. It's analytic. So anyway, here's formally the maximum likelihood. Argmax means I'm finding the beta here, the vector of coefficients that will maximize the log likelihood with respect to all possible values of the betas. Again, if you don't care about the computation part, how it does this, you can just think of trying a grid over all possible betas, and it'll find the one with the highest likelihood, right? Sometimes that's the way you have to solve likelihoods. That's not common, but you have to just do like a grid search. In this case, we don't have to, but and if I'm just writing this out now, this is what it looks when I do that. Take the derivative and set it to 0, and then solve for beta hat. Well, not yet. It's just the same as this, right? So the log likelihood looks like this. And then just doing a little bit of algebra. So it's the sum of the squared residuals, right? I'm minimizing. Oh, it's just right here. Never mind. This thing is a squared residual. Right? It's the observed minus the predicted based on whatever betas that you're trying out squared. And that in itself is called the mean squared error. So you can think of this as maximizing the likelihood is minimizing the mean squared error. And that's ordinary least squares. I mean, that's what you're doing. That's why it's called least squares. Because you're minimizing squared residuals. I just put that in for this predicted based Yeah, predict based on the beta. So if you want to take, this is, again, just trying to make it more tangible if you care about the math, and it's just a simple regression of only two coefficients, and I can define my log likelihood, it looks like that. And then I take my score equations, I get 1 for beta 0, it looks like this, and 1 for beta 1, it looks like that. And you can show that the solution is this thing here. So in other words, I don't have to go through a search of the betas. I can solve these score equations directly, and I can get beta on one side and all the data on the other. And so I just plug and chug here, and that gives me my estimates. And the important thing is I can show that this is unbiased. So the expected value of the beta hats, in this case a beta 0 and a beta 1, is equal to the true values. And if I repeatedly did this and got my different estimates every time and took the mean of the estimates, that would go to the truth as I do this over and over again. So it's unbiased. So sample size gets bigger, beta hat will go to beta true, using the law of large numbers. So it's unbiased, and that's unbiased regardless. When you show that, it has nothing to do with the distribution of the error term, except the only thing it has is that the mean of E given X has to be equal to 0. But I don't have to specify its distribution. It's normal or whatever, and I still have an unbiased estimate equation. So then you can show, I might have motivated this to maximum likelihood, but I can use it where I don't have to define the likelihood anymore. I just treat it as an estimate equation. And this is the general way you can just treat them as estimated equations, and you can also don't rely on the distribution when you get your inference as well. And that's what's called robust inference. So we're not looking just at linear. We want this to be true for whether we're determining linear, logistic, Poisson, etc. So this is like linear, logistic, log linear. And meaning we can, again, I did this early in the course, but when I can write that there's, the important thing is G here is some link function, either identity in the linear case, I don't transform the linear part at all, logit linear in the logistic course and the logistic case, and log linear in the Poisson log linear case. So G is called the link function, and that's how we make sure the model is proper. It assures that is, no matter what I put in for the b's and the coefficients and the x's, I will get out a predicted value for the conditional mean that respects the natural bounds. In the linear case, there are no bounds. In the logistic case, it has to be between 0 and 1. Like the mean of a binary outcome has to be between 0 and 1. And the log linear case, it has to be 0 or greater. The general form of this looks like this. So you get the estimating equation for all of them. That's the general form. Don't worry about that. But it involves the derivative of the linear portion with respect to beta. Then you have the betas, and then you have the inverse of the variance covariance estimate. And because the way they do this is called iteratively reweighted least squares. That's how they solve the GLMs. In the linear case, of course, we don't have to do that because this weight is the same for everyone. They're assuming constant variance, for instance. So 1 over a weight that's 1 over sigma for every person means it doesn't do any different. It doesn't reweight them. So you can ignore that. It's for the binomial, 1 over the variance is the mean times 1 minus the mean. For Poisson, it's the mean, right? So these will change as you change your particular family you're looking at. But they all have this form. And that's why they call it generalized one of the reasons it's called generalized linear models, have a very general form for the solving the likelihood. And they all have this property that even when you ignore the distribution of the outcome per se, but use this, they're unbiased like estimating equations. So that's why you can use them to do estimation without specifying the likelihood. That's something else to say, but I've gone. Anyway, this is just a class. This is like a very, very very short. Oops. Why is it doing that? Of just generalized linear models. And this isn't the only ones. There's other generalized linear models that could fall in this class that have what's called an exponential form. But in a nutshell, for this class, this is tries to give you some explanation for where we're going now, where we're just going to use these forms of the score equations to justify an estimation where we're not going to worry about the joint distribution of the outcome, let's say. And we can do that because of the unbiasedness of these estimated equations. There's whole books written on GLM, including one called GLM. You're welcome to read it. I think it's kind of a waste of time a little bit, but because it's really not that. This is, I think, pretty much all you really need to know. There's things about, lots of stuff in like proving the concavity, the likelihood, and the guarantee that you'll find a maximum likely solution. There's, theory in there that's useful, but for the most part, practically, this is what it is. Okay, so now we're taking the leap that we really just ignored the fact that we have repeated measures and we'll have residual correlation, so the y's aren't independent, even though I can treat them way in the estimating equation, still get unbiased estimates of the coefficients. What we want to do now is modify how we get the inference so it accounts for it. Because we've already shown that if you ignore dependency between the outcomes and you just treat them independent, you get biased standard errors, right? So we have to fix that the way it's done in a way that's general and also doesn't add hopefully doesn't add as few assumptions as possible. So we get standard errors that are so-called robust. So here's the general form. These are all now like vectors and matrices. Don't worry about that. This is a general form for repeated measures. I can represent it as a sum across individuals' data. Remember, I is going 1 to m. So these things are, they're vectors of partial derivatives, and these are matrices. Now, it's not that important. It's just that I can have a general form that represents it this way. And now we have to, particularly we get our inference, we have to estimate this thing because the inference is a function of the variance-covariance model for the outcome given covariance. Or if you're in a linear case, you can think of the variance-covariance of the error term. So this messed up, but this right here, wow, this is really bad. Why did I do that? So is this better? Anyway, this should be shifted up, but whatever. So this is the variance covariance matrix for one, yi is a vector, right? So yi is equal to like yi1, yi2, all the way down to yi(ni). So whenever I do like a variance of a vector, that means it's a variance covariance matrix, just by definition. That means I'm getting the variance of a vector means you're a matrix where you have every variance of every yi and all their covariances, right? So it turns into a vector, a matrix. So this is ni by ni, the number of observations on a person times the number of observations on persons. It's symmetric. So like if I flip it over the diagonal, it's the same numbers. And along the diagonal, there's the variances, right? I have the variance of the first observation, the variance of the second observation. And then on the off diagonals, I have the covariances between them. Because now I'm assuming they're not independent anymore. So now the variance covariance matrix is defined by both variances and covariances. Just a note, I'm using this, it really is conditional covariance. It's after we adjust for the x's, it's the residual covariance. Anyway, I don't always use that notation because it just gets so messy, but so that's what I mean. This is the context of regression. I'm regressing the y's versus the x's, and I'm looking at the residual covariance between the y's given the x's. And that's not the same as the marginal if I don't condition on the x's. Here. So how do you get an estimate of this variance? Because we need it, as we showed earlier in another lecture, you need the estimate of this thing to get the standard errors. And again, in simple linear regression, that you would just do using the LM and R, or regress in Stata, where you don't tell it's repeated measures. It assumes something. It assumes the variances are all constant variance. It also assumes the covariances are all zero. And it carries through those matrix observations to get that estimate of the V, of the variance covariance of an observation given all the covariance measured at each time. So notice that the covariance, whoa, this thing is really acting weird. Okay, here we go. The covariance between two observations on a subject, I just picked the first and the second, but is equal to the standard deviation of one times the standard deviation of other times the correlation. So the correlation is the covariance divided by the standard deviation of one times the standard deviation of the other. It's a definition of correlation, okay? And the why that's important here is for GEE, it actually uses the family that you put in, whether it's binomial or Poisson, it uses the variance model. So it doesn't independently estimate the variances of each observation as separate from the model. But it assumes nothing about the correlation. So you can also get fully robust where it assumes nothing about the variances and the covariances. But the standard G implementation is what's called semi-robust because it does assume the variance model. And we'll learn about ways to even drop that assumption. But basically, so it assumes a variance model. That is, if you're doing linear, it assumes the variance is constant. When you're doing logistic, it assumes the variance is the mean times 1 minus the mean. When you're doing Poisson, it's the mean. And those are all model-based, right? So it doesn't have a separate way of estimating the variances there. You can do that. That's fully robust, and we'll talk about that, particularly when you get the apply part later. So again, if I have logistic, so again, just to remind you, because I know it's, okay, all right, can't find it. So again, just a reminder, we often think of logistic regression being a model for the probability, but with a binary outcome, the probability is the mean. right? The expectation of y is a proportion. So you can just, I just stick with the mean notation, but in case you're uncomfortable with that, it's the same if I put the probability of ij equals 1 given xij. So here, let's say this is my model here. And again, the linear part I always call m xij b. So it's a function of the covariates and the coefficients. The standard deviation by the model. So in other words, once I have an estimate of the mean, it's going to estimate the variance using this standard deviation here, which is the square root of p times 1 minus p, or square root of e times 1 minus e. And so I can write the covariance this way. So in other words, it's going to build this behind the scenes. You don't have to remember this. And then it's a function of these things which are known if the mean model is known. And then this part, which is unspecified. So this is treated as function of the mean of y given xij. And this is unspecified. Specified. And that's the way the process is separated out. So when it's deriving these variance covariance models, which it needs to get the inference after it's done fitting, it also it uses the known relationship between the mean and the variance in the model, and then it has also then separately estimates the correlation. And it does that on the residuals. So that's the way it forms. So you need an estimate of this thing in order to get that whole variance covariance. And it starts, before it gets to the inference part, it starts by allowing you to specify a working correlation, which means it doesn't believe it's true. It's just a way to get estimates that maybe are a little more using the correlation, the estimation part. So this is an important distinction that I should have made before. There's two kinds of correlation you worry about when you run GE. The first is a working correlation that you specify that's used in the estimation part. And then there's the non-parametric estimate of correlation, which it uses to get the inference. So you can do a model where it just assumes independence when it estimates the coefficients, but then accounts for correlation. I mean, when it gets its estimate of coefficients, but accounts for the correlation when it does the standard errors. And that's always important to remember at GE. It's got two forms of correlation. One is used in estimation, and then a separate one is used that doesn't assume anything, that is used to get the standard errors. Because it's going to plug in some version of that variance covariance matrix, and it makes no sense, just trust me, to estimate that non-parametrically when you're trying to get estimates. And in many cases, it doesn't matter what you put the correlation. Sometimes it won't have any effect in the estimation. Sometimes it will. We'll distinguish between those two. That's an important thing to learn for GE. And then afterwards, when it's got its estimates, it goes back and recalculates the correlation matrix, assuming nothing, so it gets inference that's not reliant on your guess, whether you guess independence or something else. And the working correlation matrices, since they're not really intended to get it right, they get perfect, they only give you a few choices. And oftentimes only one or two of them are relevant to any particular data set. So they're not an infinite list of these things in your GE function. They're usually 5 or maybe 4, and only typically some of them are relevant. And so that's what I'm saying here. At the end, you get a standard error, a robust one, that isn't based on assuming that working correlation you specified to get your estimates of the coefficients is true. It redoes it. So it reduces some bias in the estimate of the standard errors then, because it's not based on any particular model. So again, I can specify, you can't always do this, but in the linear case, I can specify my variance covariance for my whole data set. So this is like V of all y. So that vector, it's all my y's, all the y's from the first person, the second person, that goes all the way down to the last person. I can represent that in the linear case as sigma squared, remember it assumes that constant variance, times this block matrix. Every one of these entries represents not just a number, but a whole matrix. So R1 is the correlation matrix for observations on person 1. And R2 is the correlation matrix for person 2. And so they look like this. Here's Ri. The diagonals in a correlation are always 1, right? The correlation of a variable to itself is 1. And then the off diagonals are what you would think, the correlation between the first and the second, up to the correlation between the first and the last. So you place those in, the V's, as you go down, as it estimates things, either based on the model or at the end where we don't assume anything. And then the zeros, they're just block where they're all zeros, because they represent the covariance between two different people, and we always assume that's 0. And you have to specify that. Like you tell GE, oh, let this variable distinguish between different people, so it guarantees when it makes this matrix that it keeps the correlation among all observations between different people as 0. Right? This is all based on ID that you give it. So you put these all together, you get this. And again, we'll have situations where we estimate this in a simple way, where we're getting estimates, and then we'll re-estimate it where we put in non-parametric estimates of all those correlations. Okay. So here are some working models. This is the kind of things that you put in like, okay, let's just make a guess of what it is. The most non-parametric one is called unstructured. It's not completely unstructured in that it assumes it's the same model for every subject. And it's even going to give up that assumption later when it gets the inference. But now it assumes I'm just going to specify different parameters for everything. So correlation is always one. I just have separate estimated parameters for the correlation, the first and the second, the first and the third, all the way to the last observation. So this is sometimes you can use if you had balanced data. So everyone gets 10 observations. Maybe 1 or 2 are missing a few, but for the most part it's balanced data, you can use this estimate. You can use this as a working correlation to put in GE, and we'll show you how to do that. If I have really unbalanced data, so I have 3 observations in one person and 20 in another, and they're not measured at the same intervals, then this means nothing. The correlation of the first and second is totally different meaning for the first person and the second person, so it's no longer a possible matrix to fit. So you only can use this for very balanced data. And regimented time. Even if I had 10 observations in a person, but the spaces between them varied wildly, I would not expect them all to have the same correlation, right, between the first and the second. If there's 1 week apart for some people and 30 weeks for another person, right? So this only has really meaning with regular spaced balanced data. And it will only let you use it for that too. You try to use it, if you have unbalanced data, it will crash. This is the much more common. This is always the most common used form because it allows for correlation, but it's simple. It assumes every observation has the same correlation between any 2 observations on the same person. It was called compound symmetry. It's more commonly referred to exchangeable now, and that's what is referred to in R. So this I can use on any data. If I have 30 observations versus 2, I'm assuming the correlation between any pair on a subject is equal to the same value. So it's the most common used working model. Again, it's pretty strict, right? It assumes a lot about the correlation, so you wouldn't want to use it to get your inference where you don't have to. In inference, you can actually estimate things very non-parametrically, where you don't have to assume a certain form, the correlation structure. But for estimation, because it's not as sensitive to the estimates, except for in a couple contexts that we'll talk about, it still allows you to have some correlation. Maybe that can improve estimation, make it less variable, that kind of thing. It's usually taught as more a question of efficiency. It's different ones will give you, lower give you smaller sampling variability. And there's an important exception to that. We'll get to that, but that's when you read a GE textbook, it will tell you it's not important so much for the bias of the coefficient estimates. It's really trying to get efficiency. If you get it close to the truth, you get a more efficient estimate. You can inspire this from a simple, we've had this in a previous lecture, but if I have a simple random effects model, so that, I have E alpha I given Xij is equal to 0, for instance, I can, if I look at the correlation, so this would be the correlation of Yij and Yij prime, just two observations of the same, and J is not equal to J prime. It's equal to this. It's the variance of at the person level, the alpha I over the variance of the alpha I between plus within, which is the total. So it's, between over total variance is equal to the correlation in this case. So this particular model, we'll come back again, this is a mixed effects model. This particular one has an exchangeable correlation model. So there's one place where you do maximum likelihood, it's going to assume that's the right one. If you put in a simple random intercept like alpha I, it will essentially assume exchangeable correlation. But anyway, just one example. Another one for well-structured time series type data where, time-spaced and everyone has the same numbers of observations, like the dental data, right, where everyone's measured at fixed stages, could be autoregressive. So this is an autoregressive model. It's based on this underlying model. So this is how you sort of model the correlation of observations over time. If they're closer together, they're more correlated. If they're farther together, they're less and less correlated, right? So these are time. This would be like time 1, 2, 3, ... to whatever time in. So the correlation between person 1 and person n is this number rho raised to the n-1 power. Rho is going to be positive and less than 1. So the more you raise it to the power, the smaller it gets, right? It's equal to rho if it's only between adjacent observations. Any adjacent observations will have correlation rho. If they're 2 apart, it'll be rho squared. If they're 3 apart, it would be rho cubed, etc. So it allows for declining correlation within a subject of outcomes as the time between them gets longer. And it's based on a very common time series type model. There is a way to generalize this where you don't use, this requires that time is equally spaced. Again, you only have one parameter. It's like exchangeable. There's only one row to estimate for all of them to get that working correlation. You can have another one that isn't based on equally spaced. It could be unequally spaced, but you have to put the distance between them. So this one says the correlation is some function of the absolute value and the distance in time. So if I had time measurements, 10 minutes, an hour, 2 days, etc., it would assume the correlation is that rho raised, probably some constant here. I would guess there's some constant. It could turn into a 2-parameter family, raised to some absolute difference in the time, which allows for unequal time. I've never seen this used. I've never seen it work, to be honest. So I'm not sure how important it is. But in theory, you could use it as well. Again, for many cases, the choice of this is very small effects. And when the choice has a big effect, we have another whole complication we have to talk about, which is important but annoying. So for the most part, I don't think of this as a first order decision, but it's the options. Okay, I think I'm going to stop here. So what we're gonna do next time, so I've talked about, again, it's not super intuitive, but you have the log likelihood, score equations, those can be motivated to be estimated equations regardless of the distribution or the joint distribution of the outcomes. We've talked about working correlations and how they fit into that estimating equation. And then we're gonna talk about next time, okay, after we just summarize how you get the estimates, just describing the algorithm, we'll talk about how do we get the standard errors post hoc? Because then we're gonna have our estimates and we have to go back and re-estimate the correlation where we don't make these strong assumptions. And that's GE in a nutshell. So very much like standard regression with these couple bells and whistles to make sure you get your inference right and maybe you gain some efficiency by using a working correlation that's closer to the truth. And then I'll have an implementation lecture, so we'll go examples and things like that. Go ahead.
No, so in the GEE, what we